My name is Alejandro Pensado, and I will be discussing the Neptune Odyssey mission and entry descent trajectory design. Neptune is a prime destination for future exploration missions. As such, this study came about to develop a mission concept for a flagship class orbiter and an atmospheric probe to Neptune. The results of the study will feed into the decadal survey as NASA considers its planetary science priorities for the upcoming decade. This poster will focus on the design of the entry and descent sequence for the atmospheric probe. For the mission design, this study looked at launch opportunities between 2030 to 2040, ultimately selecting a 2033 launch date with a 2049 arrival date. This case provided the minimum delivery mass. The approach maneuver was designed to meet the atmospheric entry conditions, and for Neptune, a deployment solution was found using a hyperbolic approach. The entry, descent, and landing was done as a 3-degree of freedom trajectory analysis, with the entry vehicle and the parachute selected based off heritage flights, such as Pioneer Venus and Galileo. The probe trajectory was designed to maintain communications between the probe and the orbiter while meeting acceptable max sense accelerations, heat flux, and heat load requirements. The telemetry is only possible during descent, so the trajectory was designed to ensure there was sufficient time to uplink data from the probe to the orbiter. This communication analysis is done purely on geometry between the probe and the orbiter, which has favorable orientation once the vehicle is on parachute. A key challenge in designing this trajectory was designing the thermal protection system. The probe utilizes heat, which is the dual layer ablative system, which has been studied for this application in the past. Part of the design process was understanding the trade space of how the entry parameters affected the sizing of the TPS, while still reducing qualification risks and meeting manufacturing constraints. The TPS was sized for various probe trajectories with the objective of reducing the TPS mass and for the overall probe mass. This resulted in a trajectory designed with heat loads that are within the performance capability of heat. This concludes my presentation. I would like to thank my co-authors and thank you for your time.